Hi, good afternoon. Testing, testing. Wow, for 4 5 second delay. So, mm, so this lecture will cover about the hash table. Maybe I wait for until 3:30. I will start the lecture. And tonight I will release the assignment 4 about this hash table. So I think today I will trying to cover. I will talk about the hash table first. And I think last Monday I already covered the sequential, the time complex, the sequential search and binary search have been covered in the first half when we cover the linked list, when we cover the binary search tree. So this today, yeah, Monday I already discussed about the time complexity of sequential search or linear search. Then today I think I will first talk about the hash table, and then if maybe whatever I if time allow, I will talk about the time complexity of binary search. But this thing you have learned in the binary search tree, and I just show you the mathematics proof the time complexity of binary search at the end of the lecture, if time allowed. Otherwise, I will just go through it quickly later. Today, the topic will focus on the hash table. Maybe we wait for 3:30. I will talk about it. Then the assignment 3 will be released tonight, which means that after that you have for 15 days. I put it 15 days. So by today is Wednesday. That's mean 2 weeks later, the Thursday 11/59, you have to submit it. So for my part, I only evaluate your work in the platform. So you don't have to upload your answer in the NTU Learn. I wouldn't bother about the NTU Learn. Whatever you upload to NTU Learn will simply ignore. I will base on the platform. Whatever you submit in the platform, that is your answer. Okay? I have to remind you that there's a plagiarism check. So if you get caught, definitely I have the evidence to prove that you are cheating in whatever way you share, or you take the paperwork, or you share the paperwork to other people. If you do so, the result will be 0 straight away for your assignment. So I have to remind you that don't share your work to anyone, or help your friend to submit the work. That is even worse. Yeah. So if you do get caught, 0 marks for sure. Yeah. There's no way to appeal. Have to penalize to be fair to other students. So this thing I have to remind you all. Another few more minutes. Same thing, I will go through the lecture. If you have any question, you can post it in the chat. I will try to answer it later. Where is my, move this one to here, then I need another one. Okay. We get a new page. Okay. So this part we have covered it on Monday. So I think intuitive you also expect that the sequential search best case should be 1 constant. You always get the big theta 1. If it's the worst case, you have to check through all the nodes. Of course, you need to do n comparison. and then the complexity will be big theta n. Average, not surprising that average, if it's 1 or 2 or 3, you may do 4 search, you may do 5 comparison, you may do 6 comparison, and so on and so forth. Average, it should be roughly half. Average should be n over 2. So it's still linear, it's still big theta n for average case. The time complexity of sequential search in average case, it should be big theta n. Whether it's in the key is in the array or not in the array, is in the linked list or not in the linked list, the result will be the same. So overall should be big theta n on average. And both the worst case also, this one have been talked about it on Monday. If you forgot, if you don't know, you can review the Monday lecture. This part about the binary search I have been covered in the first half by Dr. Owen. I just want to show you the proof. This one I will talk about it later if time allowed. So, but not surprising, in the end I do all these things. The conclusion is just want to let you know that from linear search to binary search, the time complexity from linear will become logarithmic. Yeah. So this is the proper proof. So I temporarily skip this part first for today. Yeah, there are the proof whether it's the same thing. I will analyze the best case, worst case. Yeah, whether the key is in the tree or the key is not in the tree. Then on average, in the end, you will find that conclusion is still logarithmic. It's a log 2n, big theta log 2n. The time complexity of binary search in average case, on average, it is big theta log 2n. Yeah, later if I have time, I will talk about it. But today what I want to talk about, I want to focus is about the hash table. You can do the search in linear times by linear search, by sequential search. You can improve by using the decrease and conquer strategy, by the binary search, but you need to sort your data in certain form such that you can apply the decrease and conquer strategy of binary search to search the key, to search the data. Then you can improve your search time from big theta n to big theta log 2n. Then can we further improve our searching algorithm from logarithmic to the next level, probably is in constant time? The answer is yes, possible. That means it's using the hash table. Instead of, if I want to improve but at this stage, I want to improve the time, I want to sacrifice the space. I'm trying to store the data in certain way. So I may need to use more space, but I can improve my search time from logarithmic to constant time. So to achieve this, you expect that you need to use more memory, and the memory usage will probably increased significantly. So this kind of algorithm or approach is kind of a space and time trade-off. You sacrifice the space to achieve better time complexity. Yeah, so basically hash table is a kind of a data structure, is a table. Just like typical example is like your dictionary. It's a kind of a table. When you want to search, you don't need to search every single page when you search the particular word in the dictionary, or you don't have to use the binary search to search the half, then by half by half. You can straight away go to the based on the alphabet to search A, B, C, D, straight away to search those pages. So that is kind of a hash table. It's kind of a data structure, allow you to efficiently look up and insert and delete the key. So that means all the data structure we look for a few things. One, we retrieve, we insert or delete. These are three typical operations we need to do in the data structure, any data structure. So same thing as a hash table. So what is the application? Typical application people are using the hash table. One is like using it as a caching. Then there's been what some application they will preload the data in the memory as a in the cache so that you can easily access and very fast to access those data you frequently use. Database, of course, there are some database also do the similar way, make it as a lookup table. You give me the person, you give me the key, you give me the ID, I can quickly jump to that particular index and then retrieve the required data for you. And then the third thing is the counting. Another application is like we want to do sort of a statistic that, for example, I want to store all the word, but I want to store it in to know the occurrence. So every time you trying to read particular word, I will trying to have attach another additional member as a count to increase the count, so that I can find out that the frequency of each number, how frequently you use the number, or I can analyze how frequently the word appear in the document. So those are they were trying to build out a hash table. Then in the hash table there's the word and with a count. Each word they come with a count, and then they can use it to monitor the occurrence. So that then after that they know certain word is used frequently, then they will put it in certain location because you frequently use it. So you will frequently retrieve those words. Then or the data, whatever data, may not be a word, maybe any kind of data, they may store on top of it. Those less frequently used data, they will store in somewhere else because you seldom use it. Then that overall the performance will be improved because those frequently used data can easily retrieve. Those less frequently data they can store in somewhere else, which you take more time to read it, but you seldom use it. So that can improve the efficiency. And another application is cryptography. How the your password set in the computer is they may build a hash table. So they compare the hash table instead of compare the password because they want to encrypt the password, do not want to make it in public. They may use the hash table to store it at the back. Then when people key in the password, they can use the hash value to verify. Of course that in the actual cryptography is more complicated than what I'm talking now, but they definitely have some kind of a hash table inside. So what is hashing? Hashing is the process of using some hash table to map the data of arbitrary size to a fixed size. Because your data, you have so much data, eventually you want to map it to a fixed size of the array or table. So that means there's this kind of a mapping, there's a hash function. So to design a hash table, a few things we need to consider. Of course, the data itself, we need to know how the data distribute so that we can decide what is the appropriate hash function. And then no matter how you design, as I mentioned here, that you are trying to map the data of arbitrary size. Since it's arbitrary size to fixed size, and the table you have, the hash table you have, very likely is much smaller than all the possible data you can have. So in the end, when you do this mapping, you definitely encounter that there are 2 or 3 or more data are trying to map to the same location. In that kind of situation is known as a collision. You have 2 different value, but through the hash function, they map to the same slot, same number, same location, same index. In such a case, is known as collision. And how do we resolve such a collision is the problem. It is some issue we need to discuss in the hash table. And then you have the hash table, you can insert, of course you can delete. So delete a key may not be that intuitive that you can just simply delete it. Later we will discuss about it. And then you keep insert the data into the hash table. Eventually, you definitely, one day you will encounter that your hash table is full. But when your hash table is full, how are you going to resize the hash table? And that is another issue we will discuss later. So first, the most intuitive way to build a hash table is like direct address table. That means you got all, let's say I have all the key is all the possible integer number. Then I just simply create an array. That means depend how many. If your range is from 1 to 1000, that means you just simply create 1000 element array to store the data. But the actual data you have maybe less than 1000. Maybe you only have 100. Just like 1 to 1000 is all the possible key you can have, but doesn't mean that you have all the data. So the actual key maybe only part of it, maybe 10%, maybe 5%, but you don't care. You just simply create such a big table so that you can direct address. That means if your key is 3, then that means that the location to store the key is at index 3. If the key is 9, you just simply store the data at the index 9. But doing that, of course, you don't have collision problem. No two key can map to the same place. All the key have a unique location. It's kind of a very brute force. I don't care if your possible key is all the integer number. Then I just check what is all the integer number available. If it's 655, if it's 2 power to I think 2 power to 32 or something like that, I just simply create a million element array to store the data. By doing that, you will find that 80-90% of your storage is will not be in use, because your actual key may be much smaller than all the possible key you can have. So this is one very naive approach, direct address table. So people definitely start thinking that, yeah, since most of the time you don't need to use, so I may trying to make this actual key through a function to make it to a smaller array to store it. Then I can save some space, but the effect is still the same. If my hash function is very simple to calculate, can be done in constant time, then I just make a function and then make it to the get a new index and then make it to the location and then store it. I still can achieve the search time in constant time. So therefore people start thinking some hash function to do the mapping. So the purpose to have the hash function, to have the hashing, is like the objective is you trying to reduce your key space to a reasonable size. That's one reason you want to do that. And then and you need to ensure that hash function still map each key uniquely to, yeah, they will return a unique number, a unique index for you. Or you can that index can known as a hash value, code, or address. But overall, the hash function cannot be too complicated to evaluate. You still need to be able to complete in constant time, such that my search time still remain at constant, big or 1 on average. Then that is the hash function we look for. So, and then the array will become known as a hash table. And then the slot, we call it each element, each slot, each entry in the hash table is normally call it as a hash slot. But doing that implies that there's a chance that multiple key may map to the same slot, or they will return the same hash value, such that you need to put it in the same hash slot. Then that is known as collision. Yeah, collision occur, that means we need to resolve such thing. When there's a collision, what should we do? Is the problem we discussed in the hashing. One of the important issue we will discuss here. And another thing you need to know is like, since when you create a table, the number of slot will be fixed. Will be, let's say you have a hash slot. Then your data, you have n data to store in hash slot. Then there's a ratio known as a log factor. Log factor is help you to evaluate how many, you can think it's like how many percent of the slot is in use, the usage. Yeah. So if all the slot is in use, that means this alpha will be equal to 1. That means h, yeah, all the n equal to h. When n equal to h, that means all the slot. Because each, let's say each slot we only put one item. Then when your slot is full, means that you have hash slot, hash data, hash record is insert into this hash table. At that moment, your alpha is equal to 1. If it's 50% is in use, that means half of it is in use. That means your alpha will be equal to 0.5. So that is a load factor to let you judge the load of your hash table. So this is just some term. We will use it. So hash function, how do we design the hash function? A few criteria you need to consider. It can be all, you can think out all the possible, a lot of way. There's no particular function you must use. There's a lot of kind of a hash function can be used, but you need to make sure you fulfill a few criteria. This the hash function you use must make all the possible value to within the range of the hash table uniquely. That means today you provide me this number, through your hash function you return the return value, maybe let's say is 0. Then next time I supply the same key value to your hash function, your output, your return value should be the same, should be still 0. Yeah, so every time should return exactly the same value if I provide the same input, same key. Yeah, so it must be made it uniquely. Then secondly, we trying to achieve is like such a mapping is trying to distribute the key evenly, so that all the key can map it into every location, all the possible hash slot evenly. It won't be end out that all the slot, all the key will map to the same location or certain area, certain part of the hash table, and the other part of the hash table is unused. Such a hash function means it's not a good hash function. You cannot distribute the key evenly in the hash table. That means you will waste a lot of space and you won't be able to use it. So then that means that is not a good hash table function. And also third thing is need to be easy and fast to compute. Usually it should be able to complete in constant time. Normal, so the function you use likely is just a simple function calculation only. You won't be depend on the problem size. Yeah, it should be independent to your problem size. So that means you give whatever key, whatever value to the hash function, you will be complete in constant time. And also you need to minimize, because of the term, the second point, you need to make it evenly distributed, which means you also need to minimize the collision. You try not to let two different keys map to the same index. But even I said so, you cannot avoid one, because you got n data, your possible data usually is much more than the size of your hash table. So eventually, definitely there are some key will, through your match function, they will return the same value. They will return the same value, and such a situation, collision occur. So we only can try to minimize it, but we cannot avoid it at all normally. Yeah. So these are the criteria we need to consider. So therefore, there are a few examples. Yeah. Typical one is modular arithmetic, folding, mid square, or multiplicative condition method, and so on and so forth. There are a lot of method for you to choose to design your hash function. The typical one is the first one, modular arithmetic. You just simply you give me the key, I mod the hash, the size of the array you have. For example, if my size is 10, then I will mod 10. So whatever key, if the key is an integer, whatever key value you give me, I just simply mod 10. Then I will tell you that the hash, the corresponding index, the hash value. Then you just simply store the data in that location. Usually this kind of hash function, we will avoid to use the power of 10. That means your hash table, we're trying to avoid to use power of 10, 100, 1000, 10,000, and so on and so forth, because we do it based on the statistic lah. A lot of daily life data, in your daily life data, they are in power of 10. So if doing so, you will find that very likely a lot of similar data will always trying to map to the same slot. So this is something we need to avoid, to avoid it, quite simple. Try not to choose your hash table size in power of 10. Another one is power of 2, because a lot of in the digital world nowadays, since you digitize everything, a lot of data you have is likely is the pattern of power of 2. So if you store if your hash table is in terms of 2 power to n, you will find that your data also in 2 power to n. Then very likely that those data always will map to the same slot. So to avoid those things, that's why I said here is like we avoid it is because the real data a lot of time are not really random. They are not really random. Then when they are not really random, then a lot of time they have a pattern in power of 10 or power of 2. Then you will always map all your data to particular slot, always. So to avoid this, usually people will choose the size of the table is in prime number. And this prime number, try not to too close to any power of 2 to avoid the so-called clustering. All the data cluster in certain location, or always there's a collision. Even you're trying to design a very nice hash function, but your data, due to your data distribution, is not really random. Then all the data trying to map to the same place. So that is something you need to take notes when you use the modular arithmetic in the real data. Other things, other kind of a hash function you can choose, like you can trying to partition your key into several parts, and then after that you do some calculation and then combine it. You also, some people may divide the key in and then add it back. So typically people do this is like maybe your input, your key is a string, is some word or some sentence. You want to store those raw data. You may consider every alphabet is in ASCII. Then you're trying to break it into several parts and then trying to sum it up and then come out a value. Then this particular word, this particular sentence will store in the particular, will map to particular slot, hash slot. So that is kind of a folding. Also can be used, or sometimes the number is large enough, then you can try to square it and then take the middle part. Like this one, if my key is like 3121, I take the square, then it's 9740641. Then I take the middle part 406, then I just map it to 406. And there's no any specific, as long as you come out a idea to do the mapping. It's just a mapping, so you can design your own hash function as long as your hash function can uniquely map each key to a hash slot, and you can minimize the collision. You can evenly distribute the data. That is fine. Another one commonly used, probably in the cryptography also, is trying to use this kind of pseudo-random number generator method to map the key to the particular slot. For there is something like this. They time something, take the floor, then mod the the hash table size. So you can see in this example, I trying to, if my key is 1, 2, 3, 4, 5, 6 to 15, you'll find that 1 will map to 13, 2 will map to 26, 3 will map to 8. It looks like random, but actually they're not really. It's a pseudo random. In fact, the computer, the random number are also generated in somehow in this method. So just let you, this is just some option for you to choose the hash function. In the letter we talk about it, I all the example usually we will use the first one, modular and arithmetic method. We just simply mod the hash table size to map the key to the particular index. So this is the choice of the hash function. Then as I mentioned, there's a collision. There, no matter how you do it, you definitely have a chance that two different keys will through your hash function map to the same slot. Such thing called collision. But how do you resolve the collision? Here there are two options. Here there are more, but here we only introduce two. One is the closed addressing hashing. The other one is called open addressing hashing. Closed addressing hashing, also known as separate chaining. The idea is quite simple. Since they are mapped to the same location, then why not? I have a hash table. I just store all the key with the map to the same location into a linked list, and then I store the head pointer in the head pointer of the linked list. The head pointer of the linked list in my hash table. So when you search the key, your hash function bring you to this location. Then this location there's a head pointer. Then you just bring you to the linked list. When you reach the linked list, you just search along this linked list to check whether the key is in the linked list or not. Then such a method is called closed addressing hashing. So that means your address is fixed. If you give me the key, I always use the same hash function to go to this address, to this index to search the key. Yeah. So in short, that means the key are not stored in the table itself. We only store the linked list. So sometimes they also call it as a separate chaining. That means each hash slot come with a linked list at the back. Yeah. So all key with the same hash address was stored in a separate list. So search time to search the element map to the hash address definitely is constant. Then the key is how long your linked list is. Yeah. Then because the search along the linked list, you still use the linear search. But you not search all the data. You only search a segment of the data because now you have several linked lists in the hash table. So in the closed addressing hashing, address hashing, there will be alpha number of element in each linked list on average. So in my hash table is hash. You expect that so if my hash table I have hash, you can have your n can be much bigger than if you use the closed addressing, your n can be much bigger than your hash. Because I can have a linked list. So that means each hash slot can store more than one data. So if let's say as for example, every slot I store 2 data, then overall my alpha will be equal to 2. Because if every slot I store 2 data. That means I have my n is, just now I have mentioned alpha is equal to n over 2, n over h. So my n will be 2h. H is the number of slots you have in your hash table. So let's say if every slot you store 2 data, that means each linked list have 2 elements. In such case, your alpha will be equal to 2. That's what I mean, that 2 in each linked list on average is the alpha. Alpha is indicate the average number of element in each linked list. Is the average number of element in each linked list. That is alpha. The log factor will tell you on average each linked list contain how many elements on average in the clustered addressing. Okay, that is clustered addressing. So what is the time complexity? The search time in the clustered addressing. So let's say consider the worst case. The worst case means that, of course, there's a certain circumstance that even you do so, all your element, just unfortunately your data, due to some reason you have a very poor hash function, your data due to your data distribution, all the element map to the same slot. In other words, you have one long linked list and the rest are empty. Other slots are empty. That probably is the worst scenario. In the worst scenario, in such case, you are trying to do, end up, although you have a hash table, you end out your searching is a linear search, because your data all stored in the same linked list, and your search time will be same as the linear search. Then not surprising that the unsuccessful search will be in big theta n. Successful search assume that each item, each key, they can be the first item, can be second item, can be third, have equal probability. Then same thing, same as the sequential search, because it's exactly same as sequential search. You only have one linked list. All the data stored in the same linked list. All the data always map to the same slot. And now that you need to store all the data in the same linked list. In such case, not surprising that on average, whether in the worst case, in such a worst case scenario, your unsuccessful search is in linear. Your successful search on average also in linear. Then, okay, this is the worst case. How about average case? Okay, this is the interesting part. So on average, that means I also can very lucky that when I search the item is the first item. Just nice that in that particular slot, the first item in that particular slot. So can be done in constant time. I also can be a little bit unlucky, then it's a second item. I also can be a little bit more unlucky, then it will be a third item, and so on and so forth. Then worst case is what you see just now. So on average, also depend on the distribution. You can be all concentrate in one slot. Also can be in spread in different slot. So I would say on average, that means they are equally likely hash into H slot evenly. That's on average. Sometimes long, sometimes short. Overall, average should be evenly distributed. Then, so when you think about it, your hash table are evenly distributed. In other words, every slot have same number of element. Then your unsuccessful search, that's when you have alpha element in each slot. You have alpha, the log factor, alpha slot, alpha element in each slot. Let's say just now the example, my alpha is equal to 2. That means every slot have 2 elements. Then my unsuccessful search, how many search I need to take? how many comparison I need to do. If you give me the key, you want to search this particular key, I just need to do up to 2 search. If the key is not in that 2 slot, that 2 element is not in that particular, that 2 element in that particular slot, that means the key is not available. That is unsuccessful search. No problem. So the complexity, the time complexity for unsuccessful search on average should be big theta alpha. Okay, then how about successful search? Successful search, okay, this is the interesting part for this part. Okay, for successful search, you need to think about it that imagine that you haven't insert that particular key you want to search. It's right before you insert that particular key, the number of search, the number of comparison will be assumed that you haven't insert that particular key. Then your search will be unsuccessful, right? If you haven't insert that particular key. So the number of comparison you can expect that is 1 plus the unsuccessful search before you insert. So before the I item is the one you want to search. Let's say before the I item is insert into the hash table, then the average length of all lists is I minus 1 before I item insert. So should be I minus 1 is the number of element before you insert the I element, the I item, then over H, right? So this will be the alpha. This will be the alpha before you insert that I item which you want to search for it. Okay, then when I want to search the I item, that means I need to go through I minus 1 over H unsuccessful search. Unsuccessful search is big theta alpha. So I need to go through this I minus 1 over H unsuccessful search on average plus 1. The next one I will be successful. So on average, the number of key comparison over the n item, there are n possible. What is the things? So that means that it can be the I item can be the first item, can be the second item, can be the third item, can be the fourth item. I got n item. So there are n possible scenario, right? So these are all the possible scenario. Can be the first one, can be the second one, can be in another slot, can be in this slot. Then on average, it's like you need to go through I minus 1 over H unsuccessful search, the key comparison plus 1. So this is all the possible scenario. And then you divide by n. Then that's the average key comparison of successful search. Okay, so if you expand it out, then this will be plus 1. So whether it's first item, second item, or third item, you always need to do one key comparison. You found it. And then followed by this unsuccessful part. Yeah, this is your successful. Every time, whether the item is in the first location or second location or where is it, you definitely need to do one key successful one. Then the second part is the unsuccessful, but every time different. Because if it's in the first position, not surprising that you didn't go through any unsuccessful key comparison. You already found the item. But the item also can be in the second position. So if it happened at the second position, then definitely the second step is the successful one. Before that, you did one key comparison and so on and so forth. So this one is, if you expand it out, I start from 1 to n. So that means this portion is 0 plus 1 plus 2 plus ... to n minus 1. These are all the possible scenario. All the possible scenario over H on average because your data were distributed in H slot. Then I take the average 1 over n outside. Then if you sum it out, this one you 1 plus 2 plus, this one is 1 plus 1 plus 1 plus 1 n times, so it's n, n over n, so it's 1, no surprising. Then this portion, this one is an arithmetic series. So I have n term, so should be n over 2. The first term is 0, the last term is n minus 1, so it's n 0 plus n minus 1. Then outside, I got 1 over n times 1 over h, 1 over nh. Then you just simplify this, then over all, this will be n minus 1 over 2h. So this is the time complexity in average case for successful search, which is equal to big theta 1 plus this part is, you can see there's an n over h, so it's big theta alpha. It's alpha. It's a linear function of alpha. It's a linear function of alpha. So which is alpha in short. Because it's just minus 1, then there's a 1 over 2 n divided by h. So can simplify. I simplify after this step. I simplify it to big theta 1 plus alpha. So if alpha is a constant, number, overall the time complexity should be a constant, in constant. So such a closed addressing or closed address hashing, this approach is, if my alpha is constant, I keep it as constant, then my search time will be in constant. But if my alpha is not constant, then it will not be a constant. Okay? Yeah, this part need to think about it. This is a bit tricky part, because you need to think about it. The average search is like, you need to imagine that you haven't insert that particular key. Before you insert that particular key, in that environment, you definitely unsuccessful search the key. There's no such key. Before you insert it, the key is not available. The time you need to take is I minus 1 over h. The number of key search you need is I minus 1 over h, which is alpha. Before you insert the I item. Then when you insert the I item, that means the I item will be at the next location. Then you just need one more key comparison. You will find the key. For the successful search, you need to think in that way to analyze it. So then the I item, the item you search can be the first item, can be in the second position, can be third, can be fourth. On all the items have equal chance being searched. Then you need to consider all the items. You got n item. Then there are n possible scenario. Yeah. Then you sum it up. These are all on average, all the possible scenario. Then on average, you will end up is 1 plus alpha. So if alpha is constant, implied that the search time will be inconstant, whether it's successful or unsuccessful. But if your alpha is not constant, then that is different story. Then this hash table means that it's also not good. What does it imply? That means that when you build such a hash table, you need to ensure that this particular ratio, n over h, is keep it in some constant number. It should not grow. So that's why when you insert more and more data to certain point, later we need to talk about it. We need to resize the table. Otherwise, your alpha will not keep it in constant. Your alpha will keep changing. Moreover, in closed address, you can see that you can keep insert the data. The data is stored in a linked list. So that means the alpha can go beyond 1, can go much larger than 1. Because your n can be bigger than h. So your alpha can go much bigger than 1. So if your alpha beyond than is no longer a constant number, then the search time is not what you want. in the worst case is what I discussed in the previous slide. In the worst case, it will become a linear search. Then that is pointless to build such a big hash table. And now, why not you just build a linked list? If you don't mind, then why not you just use a linked list to resolve the problem? So, and this is the close addressing. Another approach is open addressing. Open addressing, then instead of create a linked list, if this location, definitely you will encounter the collision. If this particular slot is already occupied by some earlier data you insert, then they will look for alternative location. That means the address is open. They're not fixed in that particular location. If this location is already occupied, they were trying to think some approach to find the alternate location, alternate slot. So there will prompt is required. The prompt is required to search for the alternate location to insert the data, insert the key. So the key is still stored in that. In this case, the key is stored in the table itself. And if your hash table have, in this example, I have 7 slots, that means you only can insert up to 7 items. Yeah. Then which implied that in open addressing, your alpha definitely is less than or equal up to 1 only. Because your n over h, your n only can be equal to h. In the worst case, that means your table is full. So the most intuitive way is called linear probing. When you want to think out the alternate there, I will introduce 3 probing. The first one is linear probing, very, very intuitive. For example, I give you the example, I want to insert 4, 13, 19, 11 into this particular hash table. So 4, I use the simple hash function, just mod h. So my h is 7. My hash is 7. I only have 7 slots. So I just simply 4 mod 7, which remain 4. So I will insert 4 in the slot, in the index 4, slot 4. Then I want to insert 13. 13 mod 7, you get 6. So you insert it into the slot 6. 19, you mod 7 in 5. So you insert at 5. Then the key is the last one, the collision occur. 11, you mod 7, you get 4. So the first one, the collision occur. Then linear probing is very straightforward, just simply plus 1. Your I just simply, if the first one is I, yeah, that's why the range is from 0 to h minus 1. So it's like the first one is plus 0. Then now is this location, collision occur. Then I just try to plus 1. That means you will go to the next location. Will be 11 plus 1 mod 7. Not surprising, you will map to 5. This location, collision occur again. Then just simply plus 1 plus 2. Plus 2, then you will go to the next location, 6. 6 still collision. Then you go to plus 3. Then it will become 14. 14 mod 7, you get 0. Then you go to this location. Just nice that this location is empty. Then you just insert to it. So this is linear probing. But very soon you notice that in this example, if you're doing this every time, you just find the next location. Plus 1 plus 1 plus I. Plus I means that I plus 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus to h minus 1. H minus 1 will be in this location already. Then no point to carry on. If h minus 1 you still cannot find any empty slot, that means this table is already full. Pointless to carry on. You will just repeat the procedure only. So no point to carry on. And you will notice that linear probing will give you a problem. Because every time you plus 1 plus 1 plus 1, very soon you will find that if every time your key is mapped to the same location, you will squeeze into a same adjacent location. This slot is occupied, you will move to the next slot. Next slot is occupied, you'll move to the next slot. So very soon they will form a cluster. So that is known as primary clustering. a long run of occupied slot. Then doing that, you will find that those keys will take a lot of time in searching because they all cluster in the same location. And you always need to search the next one and the next one and the next one, the next one and the next one. Because all this, your key is in the next slot. So this is not a very good idea. Therefore, someone come up a little bit better solution, which is quadratic probing. Instead of just simply +1, they're trying to make it as a quadratic function. So they are not always look for the adjacent slot. So they just look for, they may jump a bit random. And yeah, for example, in this example, if I let my h is equal to 2 power to n, in this example is 2 power to 3, 8. I make it as 8 slot. Then C1 and C2, I make it as half. Then you will find that the movement is like the +1, +3, +6, +2, +7, +5, then +4. Yeah, they were not +1, +2, +3, +4 in sequence. They were kind of like a random jump. Well, this idea is good, but a few things you need to be careful. You will find that the number of slot you can have, yeah, you must choose it carefully. Your C1, C2 and H, you need to select carefully, because if you don't select carefully, you will end up that you may not be able to visit every slot by this quadratic probing. If you didn't carefully select your H, C1 and C2. So that is not what you want. Because ideally, I look for alternate slot. I would try, I need to ensure that this probing will let me try out all the possible slot. So when I try out all the possible slot, I know that only when the hash table is full, then I have no choice. I cannot insert the key. But if you didn't carefully select, you will find that you can go back and try. Yeah, if you didn't carefully select, you will find that there's certain circumstances you only can search half of it, half of a slot. The other half, this particular formula, you won't be able to reach it. No matter how, you only can reach, when you reach half of it, you will start repeat the pattern already. The pattern will repeat. You won't be able to reach the other half. Yeah, so that will be a problem in quadratic probing. And even you use the quadratic probing, very soon you'll find that because every time although you move not in sequence, in 1, 3, 6, 2, 7, 5, 4 in this particular movement, but you will end up it's still a fixed pattern. And then if it's a fixed pattern, that means your key will always insert in this particular order. When you search the key, you always will move in this particular pattern. Then that still form another kind of a clustering. Here we call it secondary clustering. If two keys have the same initial prompt, then you definitely go through 1, 3, 6, 2, 7, 5, 4. Then the sequence will be the same. That means the search time will be when the slot is insert, all the slot is insert, that means your search time will increase because you always move in the same pattern. Yeah, even you have a different key, you also insert in the, yeah, you also need to go through this 1, 3, 6, 2, 7, 5, 4. So example here, for example, this is 4. I will insert to this location, mode 8 ma. So then 13 mode 8 will give me 5. I will insert to here. 19, mode 8 will go to 3. Then 11, there's a collision. 11 mode 8 will be return 3. Then +1. Then will be here. Then still collision. Then +3. Then +3. Then will be here. Then I insert. Then that will be 11. But very soon you will realize that in this example maybe not obvious. But if you try a bigger data, you will find that you always move in 1, 3, 6, 2, 7, 5, 4. So whatever key is mapped to the same initial location, you have to go through 1, 3, 6, 2, 7, 5, 4. So your search time will increase. So people, okay, since it's so, that means I need to have a province is depend on my key. So therefore, there's a double hashing. So the province will depend on another hash function. And this hash function decide the number of steps I need to move. So that's double hashing. Then you will find that this one, the province will be random. Was sort of a random, not exactly random, but sort of a random. And this one you need to take notes is like you need to make sure that your size, your hash table size must be prime number. Must be prime number. Then in this example, same example, I'm trying to insert 0, 4, 13, 19, 11. If it's 0, you mod 7. Then of course you map to 0. Initially no collision one because your table is empty. 4 you also map to it to this location. Then 13 will map to 6. Then 19 you will map to 5. Okay, 11 the collision occur. You map to here, there's a collision, right? So if there's a collision, your 11 you go and mod 3. 11 mod 3, you will give you 2. 2 plus 1, 3. So I plus 3. I just need to move 1, 2, 3. 3 steps will be here. Will be here. Okay, this location, there's a collision. So you just move another 3. 1, 2, 3. So should be here. So this is the next location. I prone it the alternate location. Since this location is empty, then I just insert my 11 here. So that is the double hashing. You'll find that every key they will get different kind of a prompt to look for alternate slot. Then there will not be a fixed position. Then your search time will be more will not be, there's no, not easy to form a cluster. I would say not easy to form a cluster. Then your search time will not become a linear. So that is why people like the double hashing. Okay, so one thing you need to take notes here is like you notice that you cannot anyhow select this hash function. You think about it, why I need to plus 1? Do you have any idea why I need to plus 1? If I don't put plus 1, the consequence is like you will find that if I don't plus 1, there's a chance this mod 3 will give you 0. Then you always will stay in the same location. So you will find that this one will always is either plus 1, minus 1, or whatever. You need to make sure that you won't end up that this particular prompt function give you 0 because you will stay in the same location. You also need to make sure that this thing, why I need to choose the prime number, is ensure that you give me whatever number here is not the factor. It cannot be the factor of the slot. Otherwise, I need to ensure that I still need to be able to visit every all the slot in particular sequence. But in the end, I need to visit all the possible slot once. So that's why they need to choose the prime number. Yeah, so this one and earlier one is different reason why I need to choose the prime number. Earlier is due to the real data. I need to choose the prime number. Here I choose the prime number is because I need to make sure my prompt be able to visit every alternate slot, all the possible alternate slot. So the time complexity for linear province double hashing, just for your information. Yeah, I will not go to prove it. You also don't have to know how to prove it. But if you want to know how to prove it, you can check this particular book by this person. This is a very well-known person. All this matter is think by him. Yeah, he's still around. Yeah, he developed this thing in 1973. So this is a quite well-known book in computer science. You can go and read it. The thing I want you to take notes is like this, but all this time complexity is the function of 1 over 1 minus alpha. 1 over 1 minus alpha. What does it mean? when your alpha close to, because for open addressing, your alpha only can be must be less than or equal to 1, right? So when it close to 1, then your time complexity will grow very fast, will go very high. Yeah. When your alpha is small, so we need to keep your alpha as small as possible. Usually we try not to go beyond 50%. The slot, yeah. So then that will consider your search time still can remain at constant. Then the next one is the delete key. If you want to delete the key, it's not that simple, because for open addressing, for close addressing, it's quite easy. You just simply delete it, no problem. Just like you delete the key, anything from a linked list. But delete a key in the open addressing, you need to be careful, because if you delete the key, you don't do any marking, then when you search it, you search the key, you may miss the things because your slot is empty. But actually it can be the after this particular slot, there's an alternate, there's a other key behind. If you miss it, if you left it at empty slot, you won't be able to search the subsequent key behind it. So usually they, instead of really delete the key, we don't do the delete. We make a marker, indicate that this slot is deleted, not this slot is empty. So this thing you need to be careful. I think my assignment there, you need to think about it carefully. Yeah, look like just make a marker. Yeah, it's different from deleted slot, and empty slot. There's some different. Yeah, you can't. Yeah, we'll make a marker, indicate that this slot is deleted. This slot is not empty. It's different from empty. Empty is you never insert any key here before, but deleted slot is there are something before that. Yeah, so next time you insert a new key, you can override it. But when you search to this location, you cannot assume that it's empty, so no more things behind. You should carry on your search, because your key can be after this. Yeah, so yeah, you can override the new key onto this slot. If you want to insert, of course, you will try to override it instead of insert into the next empty slot. But even you do that, if you too frequently delete the key in the hash table under the open addressing, very soon your search time will increase, because you're always reaching the deleted slot. In such a situation, we may need to do the garbage collection. When you delete too many data in the hash table, and always your search time increase, because you always need to spend a lot of time to reach all these deleted slot. To improve it, very simple, you need to rehash it. To rehash it, or your table rehash is, one is this garbage collection, another one is your table is almost full. Then you want to increase the size to such that you can insert more data or do the garbage collection. When you realize that your alpha increase, especially under open addressing, you want to increase, very simple, just create a bigger hash table and then remake all the key in the original hash table to the new bigger hash table. Yeah, normally we wouldn't do this too frequently. When you want to do this, you better one time you just increase the size to double, triple. You don't just increase one or two empty slot to lower now your alpha a little bit. Then you need to fix, because every time you do this is you need to reinsert all the key. Yeah, so it's very time consuming. Yeah, so we try not to do it too frequently. So when we want to increase the size, we straight away double the size, double the table. Okay, I think today I think a bit overrun, sorry about that. So today I just cover the hash table. So you need to know that to do the hash table, to do the hashing, is we want to improve the search time from linear to logarithmic to constant time. But doing that, you need to sacrifice your space. You need to use more space. You need to create a very large hash table to store the data. Then there are a few ways. There's an open addressing and close addressing. We introduce close addressing, very simple. It's just like each slot they attach with a linked list. Then your data, when there's a collision, when you have two keys met to the same slot, you just store in the linked list. Such a close hashing is like will give you the log factor more than 1, can be more than 1. Then another one is you find open addressing. Open addressing is if this slot is already occupied, collision occur, you just simply use linear probing, quadratic probing, or double hashing to find the alternate location. If alternate location is occupied, you just find another alternate location. You will keep finding every possible slot in the hash table until you reach an empty slot. So because of that, you need to be careful when you delete the key under the open addressing, because when you delete the key, you cannot simply empty it. Because when you search, you will miss the key. So to do so, when we delete the key, we don't really delete the key. We just make a marker, indicate that this slot is earlier that's occupied, but right now is empty for you to overwrite the new key. But when you search, you cannot stop at this deleted key. You have to carry on, because behind you still have to carry on your probing, because behind your key can be after this. Yeah. So, and the last thing I talk about it today is the rehashing. So when your hash table is growing to certain, actually open addressing, when you reach certain point, then you, like, let's say, depend, normally like alpha is more than 0.5. I will trying to do the rehashing. I will create a bigger hash table and then trying to map the old data to a bigger hash table so that my alpha will drop. If it's 0.5, then if you double it, then you will drop back to 0.25. Then I can insert more new key into the hash table. So such a process is known as rehashing. So overall, this kind of a lookup table can let you search. If you arrange it properly, use the appropriate hash table and appropriate probing, you should be able to achieve your search time in constant time. Yeah, so that is why people if they have the data frequently used, they will use the hash table to store instead of using the sequential search or binary search. Okay, before I end this section, one question today. For assignment, will all test case be included? Yes, for my part, yes. Are they hidden? No, when you submit, you should know that they will tell you that, but I wouldn't disclose. Don't ask me the test case. Yeah, you will find that my assignment, there are something, you need to go and think about it. That's why I keep emphasize the delete key. You need to think carefully. One of the question, you need to think about it. When you delete the key, how you search the things. When you insert the new key, how do you consider the delete key issue? And don't ask me to give you the test case. I won't tell you the test case. You need to think about all the possible scenario and how to fix the problem by your own. You need to know. I think one of the things you need to learn is when you have a problem, you need to know all the possible scenario. Did you consider all the possible scenario or not? Yeah. So, well, I didn't have a hidden test case. And you also don't need to upload the answer in the NTU Learn. I only use the platform to evaluate your work. Yeah. So any other question before I end the section? Maybe later I will put another. Maybe later I spend another half an hour to go to go through the binary search. It's just showing the proof lah. before that, I think you already know that the binary search is in log2n. This few slides just show you the give you a more proper mathematics proof on the binary search only. But expected before you know derive the answer, you already know that binary search should be log2n. And also, okay, another thing I forgot. My assignment, there's some MCQ together with the programming question. You need to answer it. When will you release the first assignment? Tonight. I think you should receive the link at around 11 o'clock. Yeah. Then they will start the test. Try to log in as soon as possible. So what I'm doing is like the deadline. The thing you got 15 days to do. So don't ask me for any extension. Yes, after 15 days, you find that you still can submit. Maybe you still can submit. Then there's been no penalty. What I will do is like 15 days later, I will end the test anytime. When I end the test, well, I don't know. So that means I still give you some extra. I may give you some extra time. But after 15 days, anytime I can end the test. I have the right to end the test. But before that 15 days, you can do the test. After that, I will end the test anytime. If before I end the test, you still can submit it, I won't penalize you. But once I end it, you don't ask me to reopen it. I won't reopen it because it will be very troublesome. Okay? Yeah, maybe next half an hour, I just simply go through it. If you want to stay back, you can stay back. Otherwise, this video will also be uploaded later to you. So I will talk about the binary, quickly go through the binary search. In fact, you should know that when we cover the binary search tree, we already told you that the height of the tree is the number of edge on the longer path from the root of the leaf. Then the depth or level, I need to define this first, because if I don't define this, different book they use different. Some book use the edge, some book use the nodes. So I need to put the definition. I use the number of edges from the nodes to the root, means that from the nodes, any nodes, you want to know the level or the depth of the nodes, then you're trying to count the number of edge from the nodes to the root of the tree. So if that is the case, then we want to know the height. Definitely you have number of, if you have n nodes, then the n definitely is less than 2 power to h plus 1 minus 1, or greater than 2h minus 1. You can try some example like this one, 1, 2, 3, 4, 5, 6, 7. So it is level, this is the height of the tree is 2. So it's 2 power to 3 minus 1, which is 7. 7 is a complete binary tree. Yeah, your n for for height would equal to 2. Then it must be smaller. It's like 1, 2, 3, 4. 4 nodes is the minimum you can have. So is it true? 2 power to 2, 1, 2, 3, 4 minus 1. So which is 3? It must be greater than 3, which is 4 lah. And less than or equal to 7. Right? Correct. 4 to 7 ma. Either 4 nodes, 5, 6, 7. Yeah. So that is the possible number you can have. Then if you're trying to simplify this, you will find that, yeah, the height, the minimum height is the floor of log2n. So from here, actually, you already expect that your search time is log2n. Because when you search the key, any key in the tree, yeah, you definitely will move every level of every level you only search one nodes only. For binary search, you only search one nodes only. So implied that the number of search you can have in the worst case is log 2n. Yeah, because every level you only search one nodes. Every level you only search one nodes, one of them. If you notice, you can go back and analyze. So proper way, if you know the binary search we have covered earlier. So let's say this is the Tn. This part you do some compare, yeah, it's constant time. Then this part I will search n minus, the problem side when you search the left subtree or right subtree is n minus 1 is the number of nodes minus 1, the root, divide by 2. Divide, minus 1 is minus the root, divide by 2. So 2 subtree. You either, it's a decrease and conquer strategy. You either search the left subtree or you search the right subtree. So it's either one of them, if else statement. So your problem size is from Tn will reduce to Tn minus 1 over 2. So the recurrent equation, this is the recurrent equation, Tn should be equal to Tn minus 1 over 2 and do some constant time. Yeah, you do all this comparison to check whether it's equal to the key or not. So you take constant time for in each recursive call is do some constant operation, constant time operation followed by recursive call. And the recursive call you reduce to n minus 1 over 2. So in such a situation, this is the recurrent equation. Then we carry on with this one. You can carry on to the next one, the next recursive call. You expect that you will repeat the same thing. I will use the backward substitution method. So it will be n minus 1 over 2 minus 1 over 2. Then you, in that recursive call, you also do all this comparison. Then plus c, so plus 2c. Then you simplify this one, will be n minus 1. You can see n minus 1 minus 2 over 2 over 2. So you carry on to the next one, so become 3c. Then you simplify to this. You start finding there's a pattern. It's n minus 1 minus 2 minus 2 power to 2. Not surprising, there's a geometric series that come out. Yeah. Yes. Then this one will be by half. Then it's n minus 1. So you expect that you do it k times. Eventually you reach the bottom. So your k is the height of the tree. Is the height of the tree. So you at the level 1, you do one operation, you do one recursive call, then you go to second level. So you got two recursive call, 3 recursive call, 4 recursive call, and so on and so forth. After you do the k times, you reach the bottom. Then this is the last one. So this one supposed to be the last nodes already. It's only have one node, should be the last one. Then you can compare and then stop. So let me this one is 1 plus 2 plus 4 plus 8 plus 16 plus 32 to plus 2 power to k minus 2 to 2 power to k minus 1 over 2k. So this is a geometric series. So it should be this one, the summation is 2k minus 1. 2k minus 1. Geometric series. So it's n minus 2k plus 1. Because here minus 1. So after that, this one should be equal to 1. So I know that after I know this, I know that this number, this particular number definitely is less than or equal to 1 or greater than 0. Definitely is in this range. Yeah, you already reached the bottom. Either it's a null or one node. Either 0 or 1. Unlikely 0. So it's definitely in this range. Then I trying to simplify it. So I just trying to simplify this thing. So you will end up that this thing will be n plus 1 over 2k is less than or equal to 2, greater than 1. So n plus 1 should be less than or equal to 2 power to k plus 1 or 2 power to k. Then you do one more step, you take the log for every place. Then you will find that actually the k, in fact, you expect is k is the height, as I said. So it's the ceiling of log 2n plus 1. Yeah, k plus 1. This is the ceiling function. If you look at this one, if you can't remember, you go to read my mathematics revision. Yeah, that's the definition. So it should be equal to this. So this one will be equal to k plus 1. And then this one also this one also can be rewrite as a log 2n floor function plus 1 equivalent. The proof you can check the revision. It's a typical ceiling and floor function. Then this one, after that, this one can cancel. So my k is the floor of log 2n. As I mentioned earlier, k is the height of the tree. So I talk so much here. It's just trying to tell you that the k is equal to the floor of the log 2n, which is the height of the tree. So if you substitute back this thing back to this particular function, you will end up that this part will do the last step is the constant. It's only left one step, so it's equal. So this thing will equal to c plus kc. Then which means k, what is k? K I already found out by solving this part. Then I know that k is the floor function of log 2n plus 1 times c. C is not important. So overall, the time complexity of this binary search in short is big theta log 2n. Just show you the mathematics derivation. Yeah, sometimes we may have this kind of a situation, we need to do this. So this is the worst case. What is the worst case? That means you need to search all the way till reach the leaf nodes. You still cannot find the key. Then that is the worst case. But of course, you may not be always that unlucky in the worst case scenario. What is the average case of time complexity? Then that means you may search this. The key is maybe here. The key can be here. The key can be here. I need to consider all the possible scenario. So I already learned in the earlier proof that the worst case scenario, which is unsuccessful, the key is not in the binary search, in the binary tree. Then in that case, then that is the worst case. Then the time complexity is big theta log 2n. Then for successful search, in the successful search, I need to consider a few possible scenario. Is in the root, in the level 2, level 3, and so on and so forth. So I need to make an assumption first. Let's say my n is equal to 2 power to k minus 1, which mean that I have a and the nodes. Let's say I evenly insert all the key in the tree, so they will form a complete binary search tree for me. I only consider this first. Then if that is the case, I only have one node, I need to do one comparison. Then you will find that I have two nodes, I need to do two comparison. And I have 1, 2, 3, 4, 4 nodes, I need to do 3 comparison, and so on and so forth. I have one position, require one comparison. I have two position, require me two comparison. I have 4 position, require me 3 comparison. And I have 2 power to t minus 1 position, require me t comparison. Right? Level 1, 1 comparison. Level 2, 2 comparison. Level 3, you have 4 nodes, require 3 comparison. Level 1, 2, 3, 4. Level 4, you need how many? You got 8 nodes, require 4 comparison. And so overall, you need to sum it up all the possible scenario. That is, you sum it up. Yeah, you got 2 power to t minus 1 position require t comparison. Yeah, then the t can be 1, can be 2, can be 3 to k, because you got k level. Then you divide by 1 over n. Then what is this summation? This one is the what I mentioned in the previous lecture, is the arithmetic. You will find that this part is 1, 1, 2, 4 is a geometric series. This part 1, 2, 3, 4, 5, 6 to t is an arithmetic series. It's a combination of geometric and arithmetic series. You can check the notes, the proof, the formula, you can find out. But here I just use the formula straight away. So I just substitute the formula, then divide by n. Is a k minus 1 times 2 power to k plus 1. Then what is k? I have learned it earlier. K is the log 2n plus 1. Then log 2n plus 1. K is here. Yeah. Here, k. The k is, because earlier I have made the assumption is a complete tree. So my k is, you can use this one, 2 power to k minus 1. So it's n plus 1. Then you log 2n. Log 2n. So log 2n is equal to k. Then you just substitute into this equation. Well, I talked so much. In the end, this one is still the log 2n function. Because this part is constant, not important. This part is the log 2n over n. So as your n grow, then this one will be close to 0. When your n go to infinity, that means this one will be close to 0. Then this part is constant. So in the end, your time complexity on average still depend on the log 2n. And this is the, if you didn't read the mathematics revision, you can refer here. That's the proof for this kind series. It's very similar to proving the geometric series. I use the same trick. So that's when you have this series, you just simply times the factor 2. Then after that, you subtract the second equation and the first equation. Then after that, you can find that you can simplify it easily. Then you end up, you get this equation. So overall, you have a probability that you get a successful. You have another probability is unsuccessful. Whether it's successful or unsuccessful, both are log 2n. So in the end, you can conclude that binary search on average is still log 2n. So that's what I want to tell you only. But even you can't prove this thing, you also can expect that you already can expect that binary search, the time complexity is log 2n. Here it just show you a more proper mathematics proof only. That's why I don't want to go through it in the lecture today. Yeah, the purpose is let you know that in some algorithm we may encounter this kind of series. Yeah, so we may use this. I just want to take this to show you that, yeah, if you encounter this series, yeah, you can solve it in this way. You may encounter it because time complexity, you do the recursive function like just now what you see. Every time you reduce your problem by half, you do it k times, end out you very likely you will encounter this kind of a series. Okay, so I will end this video, and this video will upload to the YouTube. So I will not upload to the NTU Learn, so don't ask me where to find the video. It's in the YouTube. Okay, if no other question, I will end it. Thank you.